Thanks, everyone. So you can see some of our main co-workers here at GSWA that have helped with this interpretation, but also Michael Dublier and Andy Calvert have been quite influential in this work. So Fauna's shown you this area, but I'm now zooming in to that Midwest 1 and Midwest 2 seismic line in the central and western U&Me terrain, but also going across into the particular units of the Pinjarra origin. Dave Kelsey is managing this project. Raphael will talk about the Southwest 1 line, and Ivan will talk about the particular history of along the Darling fault system. So our work has actually moved out a little further west in recent years, covering that area, but you can see that Midwest 2 is a little bit poor on our coverage at present, but we are working to improve that over the next few years. Charmaine will talk about the Perth Basin. Dave Kelsey is actually working on the Pinjarra origin features, but we have started to make inroads into that in terms of the 3D architecture based upon what we see, especially in Midwest 1. So I'm saying under the boxes there, we built this from a huge number of constraints from multiple types of geoscience. And I feel very lucky to be part of a team that actually talks to each other about deep geophysics and going all the way from our varied mapping in the Archean, different types of Archean crust, and our expertise in geochronology and geochemistry, in particular with basalt and granite geochemistry data sets being very important, and also the isotopic maps and metamorphic data that you see on the back wall there. We have integrated across a wide variety of geophysics, and we've used some of the results from our previous active seismic interpretations. There's also this added complexity, which you'll see on those lines on the wall there, that there's a lot of Proterozoic dike influence in these data sets. And our limited but progressing understanding of the Proterozoic origins. And later in the day, Charmaine will cover the Phanerozoic basin architecture, but there are also basin components to the Proterozoic origins. We designed these to help with an east to west traverse across the craton, especially in Southwest 1, but from YU2 to YU3, joining to Midwest 1, we've actually HiSeis have reprocessed across there so that we can seamlessly look across those regions. The main questions we want to ask are essentially, how does our knowledge at the surface extend at depth? And one puzzling feature which we've been trying to address is the origin of these red and orange patches in the Western Yilgarn on the gravity image. What is the origin of that? And also those red blobs on the far west there are likely the highs of the Proterozoic origin, and how does that relate at depth to the Darling Fault and the Perth Basin? We also have the opportunity in Midwest 1 to cover regions that have experienced vertical tectonics at the Elgoo Dome and contrast that with more transpressional tectonics in the central U&Me terrain. And also pose the question, what is the relationship to mineral systems at depth as well? I'll cover the framework we've developed from mapping and geochronology, which is this very complicated chart, but essentially, if your eye just is drawn to the center of that chart, you get the most voluminous events in the U&Me terrain around 2.8 billion years ago in the Nori and Palel groups, which are mainly basaltic, but also in the giant layered intrusions and the very extended history of granitic suites, which we have defined using geochemistry and geochronology as to enhance that understanding. But then more recently, I've just blanked that out because it's only the last few years we've really developed an understanding of the older stratigraphy and the older basement. But there's a more complicated story there because in orange, when you expand that timeline, we've also started to find some evidence of even older basement outcropping at the surface in the You&Me terrain, which is a characteristic previously only thought to be found in the Narrier terrain. Let's zoom into one of these central greenstone belts as an example of what we can see in this stratigraphic framework. You can see the MW1 line traversing through Yalgoo in the north, but you can see a dome and keel kind of architecture for granitic rocks. This is the Yalgoo Dome in the middle, surrounded by older greenstone belts and some of this much older Southern Cross supergroup there at around 2.95 billion years old. And the composition of those rocks is mainly basalt, but also with significant banded iron formation. And then those red stars indicate very few examples, but now something we're targeting, which is examples of 3.3 to 3.5 GA basement in these regions. The Pinjarra origin, we know a lot less about this, but essentially it contains a lot of around 1 billion year old rocks, including the famous garnet cordierite gneiss, which is a metasedimentary component of that inlier. And then the mafic gneiss and also a younger dike suite. So that's kind of summarizing our limited knowledge of the Pinjarra in these lines. I want to cover some of these dike suites here and show that in the magnetics, these appear as northeast trending, steeply dipping features in the Eramag, and this is close to Geraldton. This is the Darling Fault. The Perth Basin is a bit more diffuse there, but then as you move into the Yilgarn Craton, we probably have about 4 dike suites visible there. And if I go a little bit further further east, you can see some of these very odd-looking, but these features here in the mag have been mapped at the surface as very shallow dipping, saucer-shaped, irregular features of sills, and you can see that in those, especially the MW1 seismic line. And we also used the gravity data to produce a forward model of the Midwest lines. And here's an example. Here's the work that Steve Stark did for us on that, showing some of the densities that were used and the scale there. The color chart is from high in reds down to low in blue density values. And we were able to do that. Sorry, that's just indicating that the gravity gradient that we see, which in profile, going from a lower gravity response in the central You&Me terrain, and at the Darling Fault, you actually get relatively high gravity values. So our challenge was to map that and model that in a 2-dimensional forward model. We used constraints from existing seismic lines for particular lithologies and suites of rocks, such as TTGs and greenstones. We also had new measurements from drill core, and some for the lower crust where there's no exposure, and for some of the lower levels of this modeling, we have had to use a more kind of a global data set, which indicates appropriate densities to be using. And one thing we noticed is that the Bold Rock Supersuite is the very late cratonization granites, which I'll show you some examples of, but we actually see an increase in frequency of those in the seismic lines as we move to the east. And these are one of the lowest density units that we have. So that I feel is contributing to this lower gravity in the interior of the UME terrain. I'm really just advertising future talks here because, for example, the metamorphic talk and poster coming up from Riley is going to show this interesting new data set, which uses a lot of qualitative analysis of petrographic reports from across the Yilgarn. And as you can see, it has highlighted a very interesting corridor here on this western margin of higher grade metamorphic rocks. And it is roughly parallel to the Darling Fault, but you can see the MW1 line shows a transition between these two regions quite well. And there's also a correlation with those new, more ancient basement data points that we're getting, which are around 3.3 billion years old. And then Rose's talk later on and her poster there will show this is just one example of what we can do with these isotopic maps. I'm sure you've all seen this before, but also drawing your attention to that western margin of the Yilgarn and how some of the most radiogenic and some of the most ancient basement signals are coming from that far western margin. And the seismic lines there, MW1 goes through from an older region into a more a region that's experienced more juvenile input, and that is called the Q isotopic zone, which goes down to a kind of a 2.8 GA juvenile signal there, which we correlate to those main magmatic events in the central UME terrain at 2.8 GA. So I'll touch on now, again, topics you'll see in the afternoon, but I'll show you what happens when you intersect these data sets with the MW1 line. This is the magnetotelluric preliminary result, which Sasha will talk about later. Jean Lee did the processing for this, but there are incredible features at incredible depths within this data set. I'm going to overlay the seismic line there so you can see where the crustal features are. The Mount Magnet Greenstone Belt on the right has its own MT response there of several conductive features, but there's this one huge clear anomaly in the uppermost mantle that is a very significant looking body that would only easily be explained by the presence of at least some sulfide. So it's a very exciting discovery there. And that red line there draws, you'll see on the poster there, but the red line shows you the difference in the lower crust that occurs around this point as well, from a highly reflective lower crust in the east to a less reflective lower crust in the west. And that feature in map view seems to trend along a particular orientation there from Payne's Find towards Q. And what does this line up with? Well, the most sulfidic unit we know about at the surface is Golden Grove, which is a giant VMS deposit which lies under there. But the question is this MT conductive MT feature related to something that's very old, or is it actually superimposed upon these older event history in the UME terrain? So there are other features there, such as a rare earth element deposit that could correlate to this, which is much younger. So the passive seismic shows us, you'll see from Hawaii's posters here, shows us that the Moho is very shallow in the central UME terrain and it deepens to the west. and all of our seismic lines show quite interesting variations in the MOHO. And the Darling fault system, looking at the active velocities, the passive seismic velocity data, indicates that the Darling fault, at least close to the surface, is steeply west dipping. There are other features in the close to the MOHO, which I'll show you on the next slide. Firstly, this slide is the receiver function analysis, which picks up the features in terms of the horizontal expression, and the MOHO there is picked up very, very strongly. The Darling fault, not so much, but there are discrepancies along that. And then in the velocity model, you can see that the Midwest 2 line clearly shows this west dipping feature. The Midwest 1 line shows some very stark differences between parts of that middle crust. So we've assigned those to different seismic provinces, as you'll see, because the reflectivity does change across that boundary in the middle there. There's the very high velocity at the Windamurra igneous complex in the far east, and there's also these low velocity zones kind of below the Darling fault. From the active seismic that we've already done in the UME lines, we see the possibility of this underlying migmatic basement extending across those lines. We see thicker greenstones compared to the Midwest 1 line and Midwest 2 lines. We also see the evidence of major dike swarms and sill networks. And we see a difference between east dipping middle crust and regions in the Midwest 1 line where the majority of these UME lines show an east dipping middle to lower crustal structure. And those batholiths of the Baldrock supersuite occur as large tabular bodies in the upper 5 kilometers of the lines. So here for example, on the YE1 line, we see this highly reflective lower crust, a lower reflectivity upper crust, and this east and southeast dipping migmatic basement, which extends in places to higher levels, and a sharp MOHO and these large tabular cratonization granites. So I'm just going to show you the integrated joined line across Midwest 1 to YE3, where you can see the dominantly east dipping lower crust there, and then this red dashed line in the middle shows you the difference between underneath the Yalgoo dome there, the YD, the transition to a more variably reflective crust in the west in the Yilgarn. And then we actually have to map, but we also have to remove those dikes to be able to see the complexity in the Archean middle crust. And that shows quite nicely that if you have to ignore those dikes, but you can see the top surface of that 3GA basement, the ancient basement, generally rises as you go to the west, which could have something to do with the gravity anomaly there. And then zooming into Midwest 1 in the far east, this is the interpretation I'd like to be able to go through with you at the poster, but that's our already published portion of YU3, and then this is the far east and central part of the Midwest 1 line, where you can see these mid-crustal and lower crustal seismic provinces. You can also see at the Yalgoo Dome there is a kind of a rising of an antiformal feature there, which we know contains some of this 2.9 GA TTGs. The TSS there is the Thunder Lara supersuite. So we can then use that to extrapolate across to other similar features in that middle crust which extend to the west. There's that boundary between high reflectivity and low reflectivity lower crust, and also we use this term, the MOHO transition zone, to show a slightly more diffuse MOHO there. Those are the two seismic provinces. And then further west, we see the Thunder Lara supersuite plutons within this seismic province. We do interpret that seismic province at the moment as the actual 3.3 GA basement, but we're yet to show that conclusively. And then with less data available, the Northampton inlier, we interpret from some of the surface constraints, such as a gently east-dipping foliation in those gneisses, and the incorporation of that dolerite, the 750 MA dolerite suite there. And the Midwest 2 line, again, we'll talk about this at the poster, but you can see a very distinctive thickening of the crust where the MOHO bows downward there. And so here's the main features. There are thrusts within the middle crust. We don't know if these are Proterozoic or not, but Raphael will show these. We have a diffuse reflectors underneath the Perth Basin, what compared to this moderately reflective upper and middle crust in the Yilgarn. And then a network of those shear zones, which we interpolate from the UME seismic lines, these dome and keel architecture near Yelgu, and superimposed by these this late sill network. So let me show you finally the distribution of mineral deposits compared to these features. We see in the greenstone belts gold and copper and PGE, and not particularly many nickel deposits here, but there is there's the Windermere igneous complex in the far east, and also the Northampton VMS deposits north of the Midwest 1 line. And in the central part there, the Golden Grove and the Jupiter rare earth element deposit as well to consider. This is the search space extended from the Julimar deposit, but also we do know of mafic intrusions in this region, and this highly conductive mantle feature running through the middle. The Gulliver greenstone belt, which is in the central part of the Midwest 1 line, is the end of a sanucatoid granite trend, which is correlated strongly with gold and copper in that region. So those are the same deposits, but now you can see it in cross section, and you can see which features of the seismic lines correlate with some of those. There's that sanucatoid trend. We don't have quite as much information over in that far western region. So our current task is to relate that history with what we can see in the seismic lines. And then underneath there is the location of the highly conductive MT feature as well. And Mount Magnet there lying on a major transpressional shear zone network. JP will talk later on about the location of the lithospheric root zone. So the results show that we do have a correlation between some of the seismic features and what could be a much larger extent of this 3.3 billion-year-old basement in the UME terrain. We also see evidence of this far west Yilgarn gravity high, and we're making some initial correlations with the mineralization corridors of the UME terrain. And we do have initial interpretations of this steeply west-dipping Darling fault and the way that it's juxtaposed against these Proterozoic, this Proterozoic margin, except I would say that the seismic reflectors in this area are quite diffuse. And if you look at the evidence there is some degree of uncertainty in that interpretation. So any feedback on that is much appreciated. Thank you very much.